please check back later today and slightly modified. So anyway, do that. So before we start today, any questions, confusion, chaos, insight into the world? Yes.
On the homework, when I tried typing things in, do you want our answers in red or black? Because I did it all in black.
You know, it would be really nice if you did it in some color, like red or blue.
Okay, so that you know that that's what
Yeah, then I don't have to hunt.
Okay, I wasn't sure.
Yeah, you know, it's any way that you can make your reviewer happy always gets them in a good mood. There was an article in the New York Times last week about the percentage of mortgages that were approved on a sunny day versus a day like this. And so we all think that we're independent of the weather, but we're not. So I always say, like, if you're going to hand in a document or something, you want to make the person who's going to be doing some work for you, you want to make their job easier. They immediately feel happier. It's just a little psychology. Science is psychology. Any other questions? Yes.
Are you posting the lecture ahead of time? Because I looked and the lecture was okay for this week's.
I posted it this morning, and then for 5 minutes I pulled it,
Okay. So
and then I reposted it because I caught an error.
Okay.
So you probably looked at it at the 5 minutes that it was down, but it was posted before 8 o'clock.
Yeah.
So, yeah. So sorry about that. Yes. I will try to post it the night before, but I'm one of these obsessive people who have to tweak everything, and it's never good enough, so I'm always tweaking it. But does it help you if I get it there by Sunday night?
Oh, yeah, nice. Please.
Okay, I'll try. Okay. I'll try to get it up by Sunday night. Any other? Jim. Oh, I thought it was. Hello? Any, is that better? Goggles, he can't be in the class, and we will provide gloves. Again, just to remind you, SI units are they're fundamental dimensions from which all others are derived, and here they are. And everything except mass, and they're working on mass, and I'll talk more about that next week, is based on something absolute and universal that anyone with the right kind of equipment could measure. Yeah.
Sorry, did you say we need goggles this week?
Next week. Yeah, so just remember to bring them. I used to give them out, but then one of the students had pink eye, and I thought, maybe that's not a good idea.
And that's for the lab, right?
That's for the lab. Yeah. And I just, go check this out. It's really a cool website. You can spend days roaming around. Oh, this was supposed to be before that slide. So you did a good job last week. It was actually kind of fun taking 50-odd people, not that you're odd, but taking 50 people who did replicates with the 1 ml and with the 5 ml. And actually, that's really fantastic. Here's the mean and the median, standard deviation, coefficient of variation, which is a way to normalize the standard deviation. So it's a standard deviation divided by the mean. You notice a little bit larger for the 5 ml pipette, and I had nasty things to say about the engineer who developed the 5 ml pipette. You know, it's inherently, by the end of it, you're going to hate that 5 ml pipette. But nice work. Here's the standard curve. There are a couple of places where people obviously doubled their measurement, but with the exception of very few data points, it's about 1 or 2% from the regression line. And so if, like NIST traceable lamps, the best they can do is 5%. Pipetting, probably 0.5%, but this is actually, if you were going to be running a lab, for business, or for basic research, you would want to know how well your instruments perform and how well your people perform. And I would say, overall, you did very well. So I think that's a good portent for the future. Now, I need a couple, maybe 3 people? Please, come on, I need 2 more. I want to show you the derivation of volume. Volume is not an SI unit. This is always a mess. This is a meter. I know Jim had it done perfectly here, of course. Okay, so you want to try to space yourselves out. So this is a meter stick. Okay, this is not a platinum titanium alloy, but it's a meter stick. So, it's going to have maybe 3 or 4% deviation. This is a meter cubed. Maybe one more person, could you become part of a human volume? And then I'm going to skip by you. So if these were completely straight, that is a meter cubed. Who has a liter bottle of water? Could you just raise it if you think it's a liter? I think the orange cap that looks like a liter. This is a liter. Do you see how big this is? How many of these can fit in here? 1,000. And so when you visualize what a meter cube looks like relative to a meter, and here written up is 1 ml is 1 times 10 to the minus 6 meter cubed. 1 meter cube is 1 times 10 to the 6 mLs, so it's 1 times 10 to the 3 liters. So when you visualize it, here is a gram of sodium chloride. This is exactly the same concentration. Here's a kilogram of salt. Could you hold that in there? So that kilogram in a meter cubed is exactly the same concentration as a gram in a liter. And I'm going to ask you this multiple times, but sometimes I think it helps to visualize. If you go to work in a seal rehabilitation center, you don't want to kill the baby seal because you got the unit conversions wrong. I was at my doctor's office and she was saying that there's a real problem because everybody's trained in the English units and then they have to give somebody a shot and it's metric. So when you go to the doctor, pay attention to what your doctor is doing. But anyway, this is exactly the same as that. And I think it helps to visualize. At least I hope. Thank you very much, human meters, human cubic meters. So there's no SI unit, but it's derived from the meter. And so that's part of this issue of being universal and absolute, and these, based on these, other things can be derived. And you also notice that part of the derivation of length depends on the derivation of second. So there's some interaction between the two. Okay, so I want you to forever remember what a meter cubed looked like. Every time you see a meter stick, you're going to think about a meter cubed. You're doomed and condemned for life. So today, the lab and the lecture are based on what is spectroscopy. And a spectrophotometer is the workhorse of chemistry. I would say maybe 25 to 45% of chemical measurements are based on spectroscopy. Whether or not it's in a research lab, in a lab that deals with manufacturing things that you use in your everyday life, it's the workhorse. And so what is the basis of spectroscopy? So I want to touch on three things. Why do some chemicals absorb light? What's Beer's law? And how does it relate to our measurement? And then how absorbance will be used in the rest of the labs for measuring the concentration of a chemical. So first off, just a review of physics in terms of why do some chemicals absorb light? So when we talk about light has that dual nature of being a wavelength and being a particle. And electromagnetic radiation, EMR, comes in all sorts of waves, wavelengths, and energy content. So here's the entire spectrum of electromagnetic radiation. And then this tiny fraction is the visible spectrum and what we would call white light. And so if you take a prism and split it, you'll see from indigo up to red and into the IR. This is for visible spectroscopy, what we'll be dealing with. There is IR spectroscopy in this part of the spectrum and UV, but we'll be dealing primarily with visible spectroscopy and the visible wavelengths of light. And the shorter the wavelength, the more energy. And that's because the energy is a function of Planck's constant, the speed of light in a vacuum, divided by a wavelength. So as the wavelength increases, and for the visible from 400 to 700, that means the energy in that photon is going to get less. So the energy is going to be indirectly proportional to the wavelength. And that becomes important for why a chemical can absorb photons or not. So you've probably seen the Jablonski manifold. They sometimes call it the Jablonski diagram. And this is the energy scale. So this is the electronic ground state orbital with various vibrational levels. An excited orbital designated as S1, S2, Sn. And the difference between the ground state and a higher energy state is important in terms of why a chemical can absorb a photon and what kind of photon can be absorbed. So it's one of these things that if you're walking up the stairs, unless you're somebody like Harry Potter, and there's a step, you can only go from one step Can you hear me? Okay. Can I give this to you guys to fix? Oh, jeez. So my point was, if you're going up the step and you're pushing weight on it, you don't push weight on it. colors. So what the LED is doing is it's adding colors. And so to create a color, it's adding colors together, whereas pigments, what they're doing is subtracting colors. And I'll show you, I think in the next slide, how that works with that green dye that you got all over your fingers last week. And so pigments are absorbing specific wavelengths, and the color that you see are the photons that are not absorbed. So spectroscopy depends on colors that are, the color you see in that green solution, that's the color that's not absorbed. So everything else is subtracted. When we have white paint, there's no absorption, so all the photons are reflected. So like if you go into a room that has a blue light, the white paint will look blue. So it's reflecting the wavelengths that are present, and it's not absorbing anything. This white on the screen, the reason we see this white is that the LED projector is projecting all the colors in the visible spectrum, and they combine together to give you white. So that's additive color, and we're dealing with subtractive color. So here's our green dye. It absorbs in the blue, and it absorbs in red. And the reason that we see green is because the light doesn't absorb. So the photons are absorbed, high energy photons in the blue, and the lower energy photons in the red are absorbed, and that gives us that green dye. So here's, this was off of a MS sheet for the component dyes. So there's actually several dyes that make up this green dye. And one of them is a yellow azo dye. So that's this pink line, and it absorbs in the blue. The other one is brilliant blue. So the color of this is going to be bright, bright blue. And notice it absorbs in the red. And so the food manufacturer puts these two dyes together to give an absorption spectrum that looks like this. And there's no absorption in the green, and so that's why the dye is green. And I'll show you another slide in a minute with the reciprocal between transmission and absorption. So the reason that chemicals absorb light is the energy of the photon of a particular wavelength exactly matches the energy that it takes to move an electron from the ground state to a higher electronic state. Well, that's the Cliff Notes version. Now, is everybody with me? So, the second thing I want to go through is Beer's law and how the spectrophotometer works. And you may use spectroscopy in different formats, but it's basically the same underlying principle. And you'll use this in 303 for measuring nutrients in the Damariscotta River when you go on a cruise. You'll use something similar in 304 in terms of measuring concentration of enzymes. So Beer's law exploits the relationship between the concentration and the absorbance. And so there's a couple of equations that at the end of this class you should emblazon in your memory. And this is one of them. So A stands for absorbance, and it has no dimensions. And you can go through this, I give you the units here, and you can see that the concentration is going to cancel. So if A absorbance is a function of concentration times something called molar absorptivity times the path length. If the concentration is moles per liter. The molar absorptivity has crazy units, and you can derive it by going backwards. It has units of liters per mole per centiliter, and length has units of centimeter. These are going to cancel, these are going to cancel, and these are going to cancel. And so absorbance has no unit. Completely unitless. So if you change, so here's the light being passed through a sample, and we give this a designation of the input light, and just for convenience we call it I sub 0. And that's what you're going to be measuring in the lab when you use an analog spectrophotometer. The light that reaches the detector we call I sub n, and this is just by convention. And so that's the light that the detector sees after some photons have been absorbed. Okay, so you have an input light, and then you have an output light. This is less than this because of absorption. So if you increase the concentration, you're going to increase the absorption, and this is going to be less. So that's what we're going to do with the green dye. And so if it's the same chemical, that's the amount of light absorbed per mole, and it's the same pattern. So you're passing the light through exactly the same path. A is going to be proportional to C. So if you are measuring the same chemical and you keep the same path length, you can turn a unitless measure into a concentration. And we do that through something called a standard curve. There's some caveats. If you put, so like, well, if you were doing a chloroplast suspension, one of the best ways to do a chloroplast suspension is put it through something called a French press, which is named after Stacy French from the 30s. And you have a metal cylinder, and you compress the solution of your chloroplast and up to 400 psi. So it's like you're going to the bottom of an Marianas Trench. And then you quickly open a spigot and release that. You completely shatter the chloroplast into very, very tiny fragments. And if you put that in the path like with the spectrophotometer, now you have scattering particles. So there are two things happening in this path. One is absorption and the other is scattering. And so scattering means light is deflected. If there's a particle in the beam, it's going to be deflected. And so that's not valid. So if you wind up in, doing a muscle suspension or something like that, you might have to centrifuge to get rid of the particles, because you cannot violate this and expect this to work. The second thing is that you're too low so that you can't see any difference between your blank and your sample. You're not going to be able to get a valid reading. If your concentration is too high and no light gets through, you're not going to get a valid reading. And this is important in terms of you have to have the same. So if I'm measuring something in methanol, I can't suddenly switch out a solution and put it in acetone. So everything has to be constant in terms of this mole absorptivity. So remember this forever, because it can actually, you can also manipulate it and not just blindly use it. So I don't want to have to do anything blind, but remember this forever. How a spectrophotometer works is different than a fluorometer, and we're going to use a fluorometer in two groups. A spectrophotometer has a light source, it has a lens because it has to be collimated light, it has a prism in order to have monochromatic light. And you're going to see a little difference between the tank and the spectrophotometer, because one is a pure monochromatic light and the other is not. So you've got a light, a lens for focusing, a prism for separating out the wavelengths, a sample, and a detector and a readout. And when you go upstairs and you look at that box that Jim has set up by the sink, this is exactly what you'll see. I'm not taking apart the spectrophotometer, but this is exactly what's underneath the hood. Straight optics as opposed to orthogonal optics. So again, you have your light source, which is considered to be 100% the light that's absorbed, and the difference between these two is the light measured at the detector. And if you go to the website, there's a handout on Hughes law. There's some great, some of these people that lived 100, 200 years ago, I think were far cleverer than some of us in terms of their ability to make instruments. This is one of the early spectrophotometers where they had a microscope. Here's their cell and a second microscope. And so they're trying to quantify things, although the detector very often was the eye. And have you ever looked at your eye, like when you sit in a room and you're really bored, and you look at one and the other? And I mean, even my eyes, one looks darker than the other. And so they were trying to quantify things using the human eye as the detector, which is pretty difficult, but some of the original chemistry was amazing. And then this was one of the early, again, early versions based on a microscope, and they would look with the eye at a reference sample and then at the test solution. And it was based on using a microscope, and again, the human eye was the detector. So you used the spectrophotometer last week, and these are essentially the predecessor using the eye rather than a photomultiplier or a diode. So here's an example of a concentration gradient similar to what you did last week. So what wavelengths are being absorbed by this blue solution? Red, orange, green. Anything but blue. So when you see green, anything but green is being absorbed. When you see red, anything but red is being absorbed. So would you dial in a blue wavelength if you wanted to measure this? My very first TA got very, very flustered when he was doing, setting up the measurement. Guess what wavelength he dialed in? He was like, I'm not measuring anything, I'm not measuring anything. Yeah. So sometimes you can, it's easy to get fooled because you're not looking at the blueness of this. The reason it looks bluer is you're removing more and more of the other wavelengths. So here's what you did last week in terms of the green dye. And so you measured absorbance as a function of the dye. It's from real data, that's all. So what's absorbance? That's what you measured on the spectrophotometer. If I add more dye, should I have more light coming out at the other end? So my absorbance reading is going up, but my light transmission is going down. So how do I get to this really pleasing relationship? You also notice one of the things that's really nice is that if I double the die, if I go from 2% to 4%, I'm doubling the absorbance. And so it's just like money. You know, we're dealing with base 10 in terms of pennies, dimes, dollars. And so this is a really nice relationship. So how do we do that? So if I add more dye and I measure the light coming out at the other end, this is the relationship that you generate. So 1 ml of dye, I read, instead of 100, I read 90. 2 mLs, I read 81. 5 mLs, I read 53. These are relative units at the detector. 10, I read 35. And so this is what's going on in the spectrophotometer. So how do I get, so that's a negative exponential. So why is the spectrophotometer reading a linear positive relationship? Have you ever wondered? It's like, how do you get something? Doesn't make any sense. So that's what you're going to measure in your tank, and that's exactly what the spectrophotometer is measuring. And we can take that percentage. So the last slide was absolute, whoops. Wasn't that high. Actually, I think I did it because I made it too simple. But if you take the value of the light after it's gone through your dye and you normalize it to the light without any dye, you come up with a relationship that's called transmittance. Some people call it transmission, but you'll see the symbol T, and so T equals the light at the detector for some concentration of dye normalized to the light at the detector without any dye. And so T equals IN over I0. And you can do that either as a percentage, or which this is percent, or as a fraction, either way. So if we normalize it, but if we log transform it and take log base 10, and if anyone here is a physical scientist, or anyone here is a fiber, in physical science they tend to deal with natural log, so that's log base E. And in any of the physics classes before the break, were you doing some conversions with log base E, doing the natural log? Well, chemists like to deal with log base 10. So if you go into optical oceanography, you would be dealing with a natural log base E, same relationship, but it's just a different base. But chemists want to be able to divide things by 10. You know, it's just intuitively easy. And the first time that Manuel and I taught this course, we spent probably a weekend arguing back and forth over email in terms of the fact that I was working in log base 10 and he was working in log base E, and finally trying to speak the same language in terms of why we were getting different results. So we take a negative exponential and we can linearize it by turning it into a log. And the reason we use log base 10 is that's going to make it easy to divide by 10 as a chemist. So now we have a straight line, but we have a negative slope. So straight lines are good in terms of, if I look at this and I want to quickly tell what's a factor of 2 concentration, it's really hard to do. It's hard for your mind to do. Now I've got this negative relationship. It's still hard for my mind to do, to say. You know, you like to think that as something is increasing in concentration, your value that you're measuring is also increasing. So how do we get out of this? Take the negative log. So now finally, this looks like something that you measure on the spectrophotometer. So the onboard processing converts a transmittance into a negative log so that you can immediately see that it's a factor of 2 in concentration, it's a factor of 2 in absorbance. I think it's pretty cool. So here's, again, something that I'd like you to be able to live and breathe. Absorbance, which we said before, is equal to the concentration times the molar absorptivity. That's just how much light is absorbed per mole. And the path length. So remember, that's one expression. The other one, in terms of how you get there, in terms of measuring light at the detector, is that it's the negative log of t, which is the same as the log of 1 over t. And we can express that in different ways. It's just rearranging the deck chair. I hope this makes sense in terms of you get a negative exponential, but you turn it into a positive linearized relationship to make it easy to measure. So finally, that's where we get it. So there's 2 things in terms of getting under the hood. You've seen, and you'll see in the lab, what the optics look like, and then this relationship in terms of concentration. So here's the green dye. Here's the absorption spectrum, with the scale over here. And here's the transmission spectrum. So where there's 100% transmission, there's no absorption, and that's the green wavelengths. So one way that you can use this very practically is, remember I said Beer's law works when you're in the linear range? Now chemists are lazy. They're anal, but they're lazy. Let's say you pick the maximum wavelength, and this is what you were reading, 630, but all of a sudden you've got a problem. And your problem is, here's the concentration, and here's absorbance. And you get something like this. You're outside, you're too concentrated. So it's really concentrated. So you can do one of 2 things. One is you can dilute it. So you get out your volumetric flask and your pipettes, and you calibrate your pipette, but first you calibrate the balance, and then you dilute it, so now you're in the linear range. Or what you can do is have another set of standard curves, and you read it at a wavelength where the molar absorptivity is less. And so now you've got a second standard curve that looks like this. And so you read the concentrated samples on a different wavelength. So this would be lambda 2, and this would be lambda 1. And you just saved yourself from the extra error of having to dilute. And it's a really handy technique if you're dealing with lots of samples with various ranges. Is we take advantage of the absorption spectrum. We can measure here rather than here. You know, another way you could change path length. And let me show you the changes in the path length. But first, when I'm talking about being outside of a reasonable range, so here's transmittance. So if we're dealing with a very low concentration up here, that's really hard to get a good measurement. If we have a really high concentration, this is absorbance of 2, and that's a transmittance of 1% light. So that's a kind of flaky. So scale and the absorbance scale, you can see how this is a log conversion. You don't want to be at a really, really high absorbance because you're really measuring a very, very low amount of light. And so that's what I'm asking about, being in a valid range. Okay, path length. So here's the path length, exactly the same. So if I double the path length, triple the path length, increase the path length by 10, I'm going to get the same exponential. If I turn this, the path length, back into, if I convert this back onto the absorbance scale, what you're going to see as a function of path length, and you're going to do that in the lab today, is that this is path length and absorbance. You're going to find that if the path length of 1 centimeter versus a 10 centimeter, it's going to be a factor of 10. And remember, here's log. So if we hold these two constant, absorbance is a function of concentration. If we change this, we've got to do a new calibration. Okay, the last point, and this will be fast, is we use this, you will use this to measure the concentration of chemicals. Here's the setup in the lab. And so this is what you'll be doing next week with a standard curve. So remember, absorbance is unitless. So if I give you an absorbance of 0.2, what's concentration quick? If I give you an absorbance of 2, what's the concentration? How do you know? How do you know? What wavelength did I use? And so you use this, we're going to generate a standard curve because this is unitless. Yeah, so there's no right answer. I put you on the spot. I thought you could handle it. And you handle it great. You're great. Yeah. So we generate a standard curve. So we turn a unitless number into information. If you look on the website, the now posted lecture, there's a few little hints on the graphs in terms of what makes a good graph and what makes a bad graph.